In this video, I give an overview of Chapter 2 and provide some suggestions that can serve as a strategy for both a teacher and a student. If we look at the different sections within Chapter 2, we find that there's really a lot of diversity for whether these ideas are used specifically in Chapter 2 or later on throughout the course. Some of the concepts are found only in Chapter 2. We have specific isolated skills that are found only in Chapter 2. Foundational information that we'll use throughout the semester, and also information that's important to memorize and apply. On the left-hand side is a progression through the different ideas and topics, and on the right-hand side is a depiction showing the different learning objectives and questions and topics that we often see within the course. The ones at the bottom are typically higher scoring, the ones at the top more difficult. Thinking about concepts that are found only in Chapter 2, these are some of the more difficult topics and questions on our exam. The experiments of Thomson, Rutherford, and Millikan, and a conceptual understanding of the mass spectrometer are concepts that are only found within Chapter 2. The experiments of Thomson, Millikan, and Rutherford, we could have the students know the scientists, how their experiments worked, and their significance. Those two of those parts, knowing the scientist and the significance of the experiment, those are relatively easy. More difficult is how the experiment worked. The learning objective of describe the key experiments that led to the discovery of electrons and to the nuclear model of the atom that were described can be pretty far-reaching. As I show here from different end of chapter questions, this can be asked in quite a few different ways, so it's understandable why this is a difficult concept. The manner in which a mass spectrometer functions, that's also a difficult concept for the students. There's a description in the chapter, an overview that gives a schematic description of a mass spectrometer, consideration of the output. This end of chapter question has two parts. The second part, sketch the mass spectrum of magnesium. We've tried to probe that with questions like this, where it's stated that magnesium consists of three isotopes. And so if you are measuring the output, what would you expect? This is a conceptual question involving the output of a mass spectrometer. Those particular questions, topics found only in Chapter 2, were conceptual. There's also specific skills that are only found within Chapter 2. Calculations involving the isotopic abundance and naming organic molecules. These are items within Chapter 2 that really have limited carryover for the rest of the course. There's a description and a formula that's given for calculating the atomic weight, an example that's given for carbon. Students don't really understand this representation, the formula, but they can quite readily understand how to use it. Here would be a representative question. This is one where students can definitely acquire the skill and do well. The second topic that's pretty isolated and used within Chapter 2 but not elsewhere is the description here for various alkanes and alcohols. There's just a very preliminary view, a very limited view of this topic. An end of chapter question is shown there. Types of things we have on exams might be involving simple isomers, questions about would this be an alcohol or not. Again, this is a topic that's limited to Chapter 2. More foundational information that will be used throughout the semester. There's quite a bit of information there. It's important that students acquire these essential skills. First one is being able to use a periodic table. Periodic table is a provided resource on all of our exams, and the more advanced students get a lot of information out of it. The novice students, far less so. So an early objective would be to really just make sense of the periodic table. Which regions do we find the metals, nonmetals, where are the metalloids present, names for the different columns from alkali metals, alkaline earth, halogens, noble gases. There's also information provided for common charges that these acquire as cations and anions. Contrasting descriptions of metals with nonmetals. All of these skills are things that we want students to acquire. If we consider just these words, sodium, chlorine, and helium, even without a listed periodic table there, I'm really confident that an expert like you would identify sodium metal as an alkali metal, symbol Na as a solid. When it becomes an ion, it becomes a +1 cation. Chlorine is a halogen. Cl2 molecule in its elemental form. The anion is Cl-. Helium, noble gas. It's unreactive. It has 2 protons. Even without a listed periodic table here, I think there's an excellent chance that you could place where sodium and chlorine were found. Helium's not listed here, but I'm really confident you could place it as well. I think as an expert, you can instantly recall this information. A novice cannot. This is an important skill, being familiar and being able to use the periodic table, that there's really a wide range of abilities in our course. Some students that have more of a chemistry background can do all of this stuff that I've listed right here on the screen. For other students, it's very new to them. Also foundational are these topics pertaining to chemical formulas, particle level representations, and naming of ionic compounds. Different formulas are communicated within Chapter 2. Empirical formula, molecular formula, structural formula. If we think about the symbolism here, NaCl solid, CO2, CH3COOH, we have examples of an empirical formula, a molecular formula, and a structural formula. The formulas themselves are symbolic representations. If we're thinking about what they represent, the particle level, it's quite different. If we're thinking about this empirical formula that's describing an extended solid versus a discrete CO2 molecule, very different. Students struggle with making sense of the particle level representation and connecting it to the symbolic. I've learned this when I've asked about MgCO2. Students in Chapter 2, having learned about CO2 being a diatomic molecule, ask me, well, is this describing now a diatomic molecule? Is a diatomic molecule somehow being part of this molecule? And that's a very different representation at the particle level than we want them to acquire. We ask questions about this sometimes on our exams, considering which of these would be more likely to be an ionic compound versus a molecular one. Here's another end of chapter question representing an ionic compound, and asking if we have the red spheres represent cations and the blue ones anions, which formula would be consistent. See if you can name it. This is going to be very important as we move on to topics later in the semester, when we're thinking about strong electrolytes, for example. If we're thinking about bonding, whether it's ionic bonding or bonding within a molecule, subsequent intermolecular forces. All of these are important and begin with this understanding of the symbol and the particle level in Chapter 2. Another foundational essential skill we want is interpreting atomic symbols, especially in terms of the number of protons and electrons present. In Chapter 2, atomic symbols are introduced, and they're used as a shorthand that can describe the number of protons, neutrons, and electrons present. So in Chapter 2, we're interested in all of those parts. We don't use symbols like this very much through the rest of the semester, but we absolutely need the skill of being able to determine the number of protons and electrons present for a neutral atom or an ion. That becomes very important when we move on to Chapter 7 and we're explaining periodic trends using effective nuclear charge. And then finally, information that's important to memorize would be polyatomic ions and common acids. I recommend students memorize the items that are in bold, the ions in bold here, for both the cations and the anions. The periodic table helps with many of these, especially many of the cations, as I see alkaline earth, aluminum 3+. I also see my different halides, oxide, sulfide, and the like. So the periodic table will help with many of these. It's important to memorize the name, the charge, and the formula. Acids to memorize, I recommend my students memorize these common ones that they'll be encountering many times throughout the course, and also make connections between the polyatomic anions and the features that I see here within the acids, nitrate, sulfate, carbonate, and the like. Now, within the book, there's a fuller description about a naming approach, how the different names are connected for various oxyanions and acids. I usually don't emphasize this at the front end of my course. For something like H2SO4, HNO3, I bet that you don't go through an entire process like this while trying to name it. I think what pops into your head right away is sulfuric acid, nitric acid. You could then add an explanation, but my bet is that you begin just by recognizing it right from the start. I think it's an essential skill that we want for the students to be able to quickly recognize these common polyatomic ions and also common acids. Finally, it's important to be able to classify different compounds, whether they're ionic, binary molecules, acids, organic molecules. We have 4 different naming schemes within the chapter. Each of these begins by first classifying it. If you can't classify it, you don't know the correct naming scheme to apply. If we look at something like this, I list here a whole bunch of different molecules, anions. I think as an expert, you could quite readily apply terms like, well, is it an ionic compound? Is it a molecular compound? Is it a cation, anion, acid? All of these are things that you can quite readily do as an expert. A novice and introductory student cannot. A question like this is an end of chapter 1 is a good question in its own right, because this is asking the students, first of all, just classify it. Do you think this is molecular or ionic? And that's an important first step. As I think about the instructional implications, first of all, I would recommend students start memorizing things ASAP. No reason to wait for memorizing polyatomic ions, the common acids, common charges that we assign for different regions of the periodic table. Acquire those skills right from the start. Emphasize that some of these topics are essential ones that we'll be seeing and using throughout the semester. No reason to keep that to ourselves. If we want students to be aware of that, let's share the information. A specific skill to master, I would say, is this calculation involving isotopes. That's one where students can get feedback if they're doing it correctly. That should be a 100% question. It's something that they can master, recognize, and execute. Making connections across the various topics. I pointed out how our polyatomic ions and common acids can be connected. Polyatomics are certainly connected to naming ionic compounds, how we represent them with a chemical formula in the representations at the particle level. There's connections between the periodic table and naming ionic compounds, connections between the operation of a mass spectrometer and the information that we get from that involving an isotopic calculation. The mass spectrometer itself is related to Thomson's investigation of cathode rays. There's a lot of connections that we can make across topics as we introduce them. And finally, it remains important to connect the symbolic and the particle level. There's a big difference between what we understand with a symbolic chemical formula and what that means with a particle level representation with what an introductory student understands. That's a skill that we're going to have to develop and use in Chapter 2 and then carry on throughout the course.